Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electromagnetic theory. In the previous video, the first video, we discussed the basic introductory concepts and the basic outline of the whole study of this whole subject of electromagnetic field theory. So in this video, we are going to discuss one of the most crucial, important part which actually laid the foundation of electromagnetic field theory. It started as a confusion, but then Maxwell solved this issue, this problem, and gave the whole foundation of electromagnetic theory by giving the four equations called as Maxwell equation, which kind of unified electrostatics, magnetostatics, and all the laws which previously were used separately. So this is called as the concept of displacement current. So before discussing displacement current, first we will look at the confusion which started all this. Okay, so for that, let us just review some basic concepts related to Ampere's circuital law. So in electromagnetism, Ampere's circuital law, it kind of gives us a relationship between the line integral of the magnetic field around a closed path enclosing a current. Okay, that path, it encloses a current, it gives us a relationship between the two. Okay, so basically what it says, it states that the line integral of the magnetic field, which is represented by B vector, around any closed path in vacuum or air is equal to mu0 times the total current enclosed by that path, or the total current is represented by capital I, and mu0 is the permeability of air, free space, or it is also called as absolute permeability. Okay, 4 pi into 10 to the power minus 7, that value. So here let us say we have this current carrying conductor, the straight conductor, which is carrying current capital I. By right hand grip rule, this is the direction of the magnetic field. So the line integral of this whole magnetic field around this closed path, this loop, it is given by this expression, mu0 times the total current enclosed by this path. Because this magnetic field, this closed path, it encloses this straight conductor carrying current. Actually, it is given by the total current, the net current, which is enclosed by that path. So here there can be many other conductors, many other current carrying conductors. So the sum of those currents, that is equal to that. But general expression is this. So where did the confusion start? So let us consider this circuit. Okay, this circuit where we have a parallel plate capacitor which is connected to a voltage source and a switch. Okay, so we have this parallel plate capacitor consisting of these two plates, and when the switch S is closed, a current flows, a current I, it flows from the voltage source and the capacitor starts charging. Now, suppose we consider 2 points, P1 and P2. P1 lies on the loop before the capacitor, on the current carrying wire or conductor, and P2 lies on the free space, the space between the two capacitor plates, in between the two capacitor plates. The choice of selection of the location of these 2 points, that is very important. Okay, P1 lies on the wire while P2 lies on the space between the two capacitor plates. So these are the direction of the magnetic fields for P1. If we take this, which is again given by right hand grip rule, where the thumb points in the direction of the current and the direction of the curled fingers gives us the direction of the magnetic field. So at point P1, if we apply Ampere's circuital law, we will get this expression. For point P1, simple B vector dot dl vector, that is equal to mu 0 I. Line integral of magnetic field is equal to mu 0 times the current enclosed by that path, which is I. And here this current capital I is called as the conduction current, okay, flowing through the wire or conductor. Now, the point where all the confusion started is point P2, in between the two capacitors. Here, at that point of time, what the thinking was that there is no current flowing from this plate to this plate. Okay, so for point P2, as there is no current flowing from this plate to the other, then at that point of time, according to that confusion, for point P2, the whole thing, Ampere's circuital law, it becomes this: line integral of magnetic field is equal to mu 0 into 0, as there is no conduction current flowing from or in between the two plates of the parallel plate capacitor. That's why the line integral of magnetic field, that is equal to 0. So here the confusion started. How a particular law which should be satisfied at each point on the circuit, it is applicable at one point but is not in the other. So Maxwell solved this problem. Okay, so this was the inconsistency of Ampere's circuital law which we see in this circuit, and Maxwell actually solved this problem. Okay, so actually what he did is that he actually kind of removed our limited understanding of the concept of conduction current, which was basically current which was viewed, conduction current which was viewed as the flow of electrons or charge that we defined as conduction current. But he gave us a new definition of current. Okay, so basically he said that in between the two plates of the capacitor, where there is an electric field set up because of the charges, positive and negative charges, which are attracted on the opposite plates, because of which there is an electric field, the rate of change of electric field, okay, that produces another current, or the rate of change of electric flux that produces another current, which is called as displacement current. Okay, conduction current is for all the other points, okay, on the conductor or the wire, conduction current flows. But in between the two plates of the capacitor, because of the rate of change of electric field or the rate of change of electric flux, because of the charging and discharging of the capacitor, this rate of change of electric field and rate of change of electric flux, that gives us displacement current. Okay, this was the explanation of Maxwell. Okay, so he kind of modified the Ampere's circuital law, which was expressed as this, okay, which was Ampere's circuital law, which was expressed as this. He modified it to this. Okay, B vector dot dl vector, the line integral of magnetic field, it is equal to mu 0 into I plus ID, where I, capital I, is conduction current flowing through the wire, and I subscript capital D, that is the displacement current, which is flowing in between from one plate of the capacitor to the other, which is basically is epsilon 0, which is absolute permittivity of free space or air, epsilon 0 to d phi E by dt, which is rate of change of electric flux with respect to time. Or alternatively, we can also express it as epsilon 0 A dE by dt, which is rate of change of electric field with respect to time. Okay, this was the expression which was given for displacement current, and this was the modified form of Ampere's circuital law, which can also be called as Ampere-Maxwell law. Okay, so this was the explanation. So how he got this expression, that we'll discuss. So now we'll discuss about the displacement current expression. Okay, that we'll discuss how we got that expression. Okay. Okay, so first let us consider the same circuit, the parallel plate capacitor circuit, where we have the capacitor and it is connected to a voltage source. Okay, and we have a switch which is closed. So here, let's say the parallel plate capacitor, it consists of two plates with overlapping area A, okay, separation distance D. So the capacitance of the parallel plate capacitor, it will be equal to C is equal to epsilon 0 A by T. That is the expression for capacitance of a parallel plate capacitor. Now, because of the migration of the charges when it is connected to a voltage source, this will acquire a positive charge, this will acquire a negative charge. This will be the electric field vector. So basically the electric field, that will be equal to the electric potential per unit length, which is the separation distance D, so it will be V by D. Now we know that for capacitor, charge Q is equal to the product of capacitance and voltage. So here we can write this Q is equal to CV, we can write it as C, we can write it as epsilon 0 A by D, and V we can write it as E into D, product of electric field and separation distance. So here dd gets cancelled, so this becomes epsilon 0 A E, this the value of charge. Now we know that current I, that is equal to dq by dt, okay, rate of flow of charge per unit second, okay, per unit time, okay, basically it is taken second, coulomb per second. So if we differentiate here, which where the permittivity of free space or absolute permittivity, that is constant, overlapping area is constant, the only thing that is variable, which is the electric field. So then it will become d by dt of epsilon 0 A E, which is equal to epsilon 0 A dE by dt. So this is basically the expression for displacement current, epsilon 0 A dE by dt, which is rate of change of electric field with respect to time. This is the first expression. Then another way which we can get the same result is through the concept of electric flux. Now we know that electric flux phi E, that is equal to product of electric field and the area, okay, it is basically expressed as phi E is multiplication of E vector dA, so it is phi into EA, okay, where this is the area and E is the electric field. So E is equal to phi E by A, okay, E is equal to phi E by A. So here from this Q is equal to, from Q is equal to epsilon 0 AE, if we substitute E with phi E by A, then it becomes Q is equal to epsilon 0 A into phi E by A. A gets cancelled, so this becomes only epsilon 0 phi E, that is Q. So again, displacement current ID is equal to dq by dt, so this becomes d by dt of epsilon 0 phi E. Epsilon 0 absolute permittivity is constant, so this becomes epsilon 0 d phi E by dt. This is another way of representing displacement current, and this is mostly used, this expression, okay. So this is the first way, this is the second way, and most often you will find the second expression, ID is equal to epsilon 0 d phi E by dt, okay, this. So this is how we got the expression of displacement current, and we got the modified Ampere's circuital law, which is now expressed as line integral of magnetic field, which is equal to mu 0 times conduction current I plus displacement current ID, which is equal to mu 0 into I plus epsilon 0 d phi E by dt. Mostly will find the modified Ampere circuital law, or most appropriately the Ampere-Maxwell law, expressed as this, okay, this way, okay. So this is the thing. So friends, so we discussed, we we derived the whole thing, how we got the displacement current expression, which is written in form of this, the most popular form, which is you will find in most textbooks, epsilon 0 d phi by dt, which is in terms of rate of change of electric flux with respect to time, or this epsilon 0 a d by dt. So what Maxwell did for the point or the region or space in between the two capacitor plates, he gave us an alternative expression for current different from conduction current, which is expressed in terms of rate of change of electric field or rate of change of electric flux with respect to time, and as a result we got this modified or generalized version of Ampere's Maxwell law or the Ampere circuital law, which is called as Ampere-Maxwell law. So for the point P1 and all those points on this wire or this current carrying conductor, this first law, this first one is valid, this mu 0 I, okay, BDL is equal to mu 0 I. And for the region or space, for all the points in between the space between the two plates, okay, of the capacitor, this law is valid. This I becomes 0, conduction current is 0 at those points, and we have only mu 0 ID, and this is the general expression which can be applied for anything. So for all the points on the wire, displacement current is 0, it becomes only mu 0 I, and for the points in between the two plates, conduction current is 0 and only displacement current ID is there. So here I is the conduction current, ID is the displacement current. These two currents are responsible for the whole electromagnetic behavior, which is expressed in terms of this. Okay, this. So this is the concept of displacement current, which will be very helpful in understanding the electromagnetic behavior, which we'll discuss in the next series of videos. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.